Good afternoon, everyone. Hope you are all fine. So, in our last class of quantum mechanics, we had discussed about the Planck's radiation law, and from there we had derived the four laws: Wien's displacement law, Wien's radiation law, Rayleigh-Jeans law, and Stefan Boltzmann law. Now, in this class, we are going further into it, and we will be doing Compton effect. So before that, I need to first share my screen. Okay. So before going to Compton effect, we need to know some facts that till now, light, it was thought of as waves because before 1905, I think, mm, light was considered to be wave because it showed some effects which could only be shown by a wave. For example, interference, diffraction, polarization. These effects can only be shown by a wave. So the wave theory of light was well established. But as I said, some phenomena that were unexplainable with only the wave theory of light. For example, you have seen the Planck's radiation law. What were the assumptions of Planck's radiation law? It was the quantization of energy. So Planck assumed that a body can emit or absorb energy only in a discrete manner. So it cannot emit energy in continuous manner. And absorption or emission takes place in discrete bundles of energy nh nu, where n is any integer, mu is the frequency of that particular radiation. These packets of energies were called quanta. From here the name quantum mechanics came, obviously. Now each energy associated with each quantum particle was given by E equal to h nu. Now, knowing about Planck's assumption to explain the black body radiation, Einstein in 1905, he suggested that light is composed of discrete quanta called photons. He named the light energy particles to be photons. The photons move through space with the velocity of light. So velocity of light was established earlier when we studied, or when they considered the wave property of light. So Einstein suggested that it has a wave property, plus it can also be considered to be a particles. The particles were called quantas, and those particles can move through space with velocity equal to the velocity of light c. So the energy of each quanta, or energy of the photon particles, were given by E equals to h nu, or E equals to hc by lambda. Now, you already know the Einstein's mass energy equivalence relation, which says that E equal to mc square, where m is the relativistic mass and c is the velocity of light. So every particle in the universe has some amount of energy, that is mass to energy equivalence. Some mass is equivalent to some amount of energy. So from E equal to mc square relation, we get the relativistic mass of photon, which is given by m equals to E by c square. You put the value of E equal to h nu there, so we get h nu by c square, or h by c lambda. Note that the rest mass of photon is m0 equals to 0. So photon has 0 rest mass, but it has non-zero relativistic mass given by E by c square. Similarly, the momentum of photon will be relativistic mass times the velocity of photon, which is c. So it will be mc. So you put the value of m and you will get the momentum will be p equal to h nu by c or E by c. Now, dependence of mass with velocity. So if a particle of rest mass, so these things are comes from special theory of relativity, which is not in your syllabus, and you don't have to know the details of it. You just know the formula which we are going to use for the derivation of Compton effect. So if a particle of rest mass m0 moves with the velocity v, which is comparable to the speed of light. This thing is very much important here. A velocity v comparable to the speed of light. Then its mass will increase, and the increased relativistic mass will be given by m equal to m0 by root over 1 minus v square by c square. Now what happens in our daily life? We do not know anything which moves with a speed which is comparable to light. For example, if you take a bullet train, suppose, so its speed maximum will be 100 kilometer per hour. And if you talk about light, what is the velocity then? The velocity is 3 into 10 to the power 8 meter per second. That is 3 lakh kilometer per second. So in our daily life, the fastest thing we see is nowhere comparable to the speed of light. So the mass is same for us basically in daily life. But whenever we talk about subatomic regions, there the velocities are sometimes comparable to light, of the order of almost 10 to the power 6 or 10 to the power 7 meter per second. So in that case, the mass is dependent on the velocity of those particles. So we already know the mass energy equivalence relation. So equal to mc square is known to us. And next, the energy momentum relation. So for a particle of rest mass m0 and momentum p, the relativistic energy relation between energy and momentum is given by E square equals to p square c square plus m0 square c to the power 4, where this part p square c square gives you the kinetic energy and m0 square c to the power 4 gives you the rest mass energy. For photons, obviously the m0 is 0. So we only have E square equal to p square c square or E equal to p into c, where p gives you the momentum of photon. So E equal to pc, from here we can also see. And for any relativistic particle, the E square is given by p square c square plus m0 square c to the power 4. Now we come to the Compton effect. Now, as I said, Compton effect was one of the effects which could not be explained if we assume classical mechanics, because what happens? So first, let me tell you what a Compton effect is. Suppose we have a loosely bound electron or free electron at rest. A photon or a light of some particular frequency and wavelength is incident on that electron. It interacts with it, and then it is scattered at a particular direction. The electron is also scattered. Now, if we assume classical mechanics, we see or we observe that the scattered photon should be of same frequency or same wavelength. But in practical cases, it is seen that the scattered photon is not of same frequency. Its frequency changes as well as the wavelength changes. This effect is known as Compton effect. if you consider coherent scattering, the scattering must be of same frequency, but the case is not so. So it was not explainable by classical mechanics. That is why quantum mechanics came in, where the incident photon was thought of a particle, or so incident photon was thought of a particle, not a wave. So here what we are going to do, we are going to find out how the frequency or the wavelength changes with the change in the angle of scattering. So as I said, there is a free electron here, which is called the target electron. Incident photon comes and falls on the free electron. The photon gets scattered at an angle phi. The electron also gets scattered at an angle theta. Theta is called the recoil angle. The incident photon had frequency nu or wavelength lambda. The scattered photon will have frequency nu prime. So obviously, what happens? The electron is at rest, incident photon falls onto it, it transfers some of its energy to the electron, and the electron recoils, and it is scattered at an angle phi with some different wavelength, which must be greater than the incident wavelength. So the frequency will be less, the wavelength will be greater, because the scattered photon must have less energy than the incident photon, as it transfers some of its energy to the recoil electron. Now what we are going to do, we will apply conservation of momentum and conservation of energy to find out the wavelength of the scattered photon. So before doing so, we need to know what are the energy and momentum before collision and what are the energy and momentum after collision. Now before collision, we see that the energy is given by E1 equal to h nu, which is the energy of the incident photon. For the electron, the energy E prime is given by m0 c square. So as I said, the energy was given by, for any relativistic particle, E square was p square c square plus m0 square c to the power 4. Now as the electron is initially at rest, so its p will be 0, because initial momentum for electron is 0, so it will only have rest mass energy. So E square is m0 square c to the power 4, or E equal to m0 c square, or I have written it as E prime, and p prime is 0. Now I have not written any vector signs here, because before collision all the p or all the momentum are along the x-axis only. After collision it changes. And now see, after collision the energy of the scattered photon E2 has become h nu prime. Similarly, P2 has become h nu prime by c. Now P2, the modulus of, actually this is the magnitude of P2. P2 is along this direction. Okay, so it is not along x or not along y. So it will have components along x and components along y. Now we talk about the energy of the energy of the electron after collision, which is given again by E prime. You can write E double prime. So E double prime is given by h nu minus h nu prime, which is the change in energy of the photon, plus m0 square c square, m0 c square, which is the energy of the electron earlier. So earlier the energy was m0 c square, and then the photon gives the electron the amount of energy h nu minus h nu prime. So that is why we have added it. Again, E prime can be E prime, which is again the energy of the electron after collision, can be written as root over of p square c square plus m0 square c to the power 4, the energy of any relativistic particle. And this p is the momentum of the electron which acts along this direction. Okay, so we have written it as p only. Now we are going to do the conservations. So first, applying momentum conservation, we get p1 vector plus p prime vector equals to p2 vector plus p vector. P1 vector was the momentum vector for photon, p prime vector was the momentum vector for electron. P2 vector is the momentum vector for photon, and p vector is the momentum vector for electron after collision. So first we will do the calculations along the x-axis. So along x-axis, P1 will be h nu by c. P prime will have zero contribution because the electron was at rest. After collision, P2 will be h nu prime by c into cos phi, and P will be p cos theta. So along x-axis, if we again look at the picture, so along x-axis, before collision we had P1 plus 0, and after collision we have P2 into cos phi along x-axis and P into cos theta along y-axis. Okay, so from here we get PC cos theta equals to h nu minus h nu prime cos phi. Now if we do the same calculation along the y-axis, before collision along the y-axis every momentum was 0. So before collision on the left hand side will be 0. What about the right hand side? Along the right hand side we have P2 into cos phi along the positive y-axis, sorry, P2 into sin phi along the positive y-axis, and P into sin theta along the negative y-axis. So along y-axis we get P2, which is h nu prime by c into sin phi minus P into sin theta equals to 0. So from here we get PC sin theta equals to h nu prime sin phi. Now square both the equation 1 and 2 and then add. From the left hand side we get p square c square because sin square theta plus cos square theta is 1. And from the right hand side we get h nu prime square sin square phi plus h nu minus h nu prime cos phi whole square, which eventually gives you p square c square equals to h nu whole square plus h nu prime whole square minus 2h nu into h nu prime cos phi. So we got one equation from momentum conservation. Now we will apply energy conservation and find another equation. So doing the energy conservation, what was the energy before collision? So before collision energy was E1 equals to h nu for photon, plus for electron it will be only m0 c square. So on the left hand side we will have h nu plus m0 c square. On the right hand side we will have E2 will be h nu prime for the photon, and for the electron we will use this equation E prime equals to root over p square c square plus m0 square c to the power 4. So we see that h nu plus m0 c square equals to h nu prime plus root over p square c square plus m0 square c to the power 4. Now our aim is to find out the value of p square c square from this equation also. So rearranging the terms, so on the left hand side we only have the term under the root and everything else is on the right hand side. Now arrange it like this and then square it. So doing these calculations, you will find the value of p square c square from here. Now we get p square c square from here. Now we are going to substitute the value of p square c square from equation 1, and then we are going to rearrange the equations. So here we see substituting the value of p square c square from equation, okay, here we have a problem. It will not be equation 1, it will be equation 3, the momentum conservation equation. So we had got one value of p square c square from momentum conservation. We got one value of p square c square from energy conservation. Equate them and simplify the equation. You will get finally this equation: 1 by nu prime minus 1 by nu into m0 c square is h into 1 minus cos phi, or 1 by nu prime minus 1 by nu is h by m0 c square into 1 minus cos phi. Now if you put 1 by nu equal to lambda by c there, you get lambda prime minus lambda equals to h by m0 c 1 minus cos phi. This is the final expression for Compton effect. It gives you the Compton shift, that is the change in wavelength when a photon is scattered by a particle of rest mass m0. Look here, the initial energy of the photon is nowhere. So the change in wavelength or the Compton shift is only dependent on the mass of the scattered, or sorry, mass of the particle from which the photon is scattered and the angle of scattering. Now as -1, or the value of cos theta lies between -1 and +1, lambda prime will always be greater than lambda. So the change in wavelength, as I said, is independent of energy. That means it will be independent of the incident lambda. It is only dependent on the rest mass of the scatterer. The quantity h by m0 c, or it is often written as lambda c, is known as the Compton wavelength. So remember the difference between Compton shift and Compton wavelength. Compton wavelength is found at phi equals to 90 degree. So at phi equals to 90 degree, we get lambda prime minus lambda equals to h by m0 c, which is known as Compton wavelength, this particular term. And for any general phi value, whatever change in wavelength we get is known as the Compton shift. And when phi equals to 0, lambda prime minus lambda is 0. That is no scattering along the direction of incident photon. Obviously, it is not scattered. When phi equals to pi by 2, we get lambda prime minus lambda equals to lambda c, which is 0.024. One correction here, the unit is not written, it will be in angstrom. So lambda c is 0.024 angstrom. So, and when phi is 180 degree, lambda prime minus lambda is 2 into this one. So this is the case of maximum possible shift. Now, when I started talking about Compton effect, we told that a free electron is at rest. But is it really possible that a free electron will be at rest? First of all, no. So we have considered the electron to be free, but it is not really free. But we are doing the calculation and getting the correct result. Why? Because the energy incident on it is so large that the bound electron or loosely bound electron can be treated as a free electron. So it gets very little much energy from the incident radiation and liberate itself, and then the whole process is done. So it can be treated practically free, not ideally. Now we see that Compton effect cannot be visible or cannot be observed for visible rays. Why? Because visible rays has a wavelength range between 4,000 to 7,000 angstrom, and the energy of visible light is of the order of 2 to 3 electron volt. The binding energy of electron is of the order of 10 volt. For example, it is given that the binding energy of hydrogen, you already know, is 13.6 electron volt. So visible light cannot liberate electron from the scatterer. So Compton effect cannot be observed for visible rays. Further, one more thing, as I said, the Compton shift is not dependent on the energy of the incident ray. Now look at the wavelength range. The wavelength is, if we take one average one, so it will be 6,000 angstrom. Now the change is given by Compton shift, maximum Compton shift is given by 2 into lambda c, which will be 0.048 angstrom. Now if you add 0.048 to 6,000, can you seriously check the change? No. So the change is negligible with respect to white light or visible rays. So those are the two reasons why Compton effect cannot be observed for visible rays. Compton effect is observed generally for X-rays, which has very small wavelength of the order of 1 angstrom or less than that, because for them the change 0.024 angstrom can be obtained or can be measured, I think. Now we talk about modified and unmodified light. Whenever for the practical purposes we do experiments of Compton effect, so it is not the case that we will have only one electron and one ray of light will fall on it and we will detect that one photon. That is not the case. We do experiments taking a bulk amount of material, a beam of light with infinite number of rays falls on it, and it is scattered by that particular material. So whatever we see or whatever we observe is an average effect of all the things. So when we see the intensity versus scattering angle pattern, we see two types of lines or two types of intensity. One intensity will be at that particular lambda, and another intensity will be at the changed lambda. That is one intensity, we will get a higher amount of intensity at the incident lambda value, and we will get another higher intensity at the lambda prime value. So it is sometimes seen that the shift, there is no shift for maximum lines. Why is the case so? It is because sometimes the photons are not scattered by the electrons, but the atoms themselves. So if the photons are being scattered by the atoms themselves, then what will be the change in their wavelength? So the change will be given by lambda prime minus lambda equals to h by capital MC into 1 minus cos phi, where capital M gives you the rest mass of the atom, not the rest mass of the electron. Now you think how capital M is greater than M0, because as I know, hydrogen atom, it has only one proton and one electron. Now one proton is heavier than the electron by 1875 times. Now if you assume for large atoms, so it will have more number of protons and neutrons. So M0 will be much higher than, sorry, capital M will be much higher than small m0. So if we replace capital small m0 by capital M, lambda prime minus lambda will be very small compared to lambda. As a result, there will be no practical change in wavelength. So those lines will be called modified Compton, sorry, unmodified Compton lines. The lines for which the scatterers are electrons, we will have a fair amount of Compton shift, will be called modified Compton lines. Now, before going back, one thing I need to share again, which is the which is the energy of the recoil electron. As I said, the electron will have some amount of energy and it will recoil. What will be the energy of the recoil electron? It will obviously be the change in energy of the photon, because the system here is conservative, energy is constant, total energy. So the energy of the recoil electron is given by E equals to h nu minus h nu prime. That is the kinetic energy of the recoil electron. Now it already has a m0 c square amount of energy as the rest mass energy. So the kinetic energy is given by h nu minus h nu prime. With this energy, this electron moves on. So if I take h nu common, I get 1 minus h nu into 1 minus nu prime by nu. Now what is the value of nu prime by nu? We can get from this relation, this one. 1 by nu prime minus 1 by nu gives you h by m0 c square 1 minus cos phi. So from here we get multiply the equation by nu. So you get nu by nu prime minus 1 equals to h by m0 c square into nu into 1 minus cos phi. And if you take the minus 1 on the right hand side, you will get nu by nu prime equals to 1 plus h nu by m0 c square into 1 minus cos phi. Now invert it, you will get nu prime by nu, which will be 1 by 1 plus h nu by m0 c square 1 minus cos phi. Put this value of nu prime by nu in this equation. It seems a very large equation, but it is a very simple one, because you have just to put the values and do the algebra, nothing else. So if you put the value here and do the math, you will get h nu multiplied by h nu by m0 c square 1 minus cos phi divided by 1 plus h nu by m0 c square 1 minus cos phi, the same term. So if I take the whole numerator as alpha, that is alpha equals to h nu by m0 c square into 1 minus cos phi, we get the equation, or the equation is reduced to h nu into alpha by 1 plus alpha, which is less than h nu, because alpha by 1 plus alpha will obviously less than 1. So we see that the whole energy of the the whole energy of the photon, h nu is the energy of the photon, and the recoil energy of the recoil electron, which is the transfer of energy from photon to electron, is less than h nu. So the whole energy of the photon is never transferred in case of Compton effect, which is contradictory to the case of photoelectric effect, because for photoelectric effect the whole energy of the photon is transferred to the electrons, and the electrons, they go out of the material and they are ejected with some amount of kinetic energy. But the case is different here. Here some amount of energy is absorbed by the electron and the electron is recoiled, and the photon, it is scattered with the rest amount of energy. So that is the basic difference between Compton effect and photoelectric effect. Now in photoelectric effect, I don't think I have much to say. So that's all for today. You study it well, and if you have any question, you write it in the comment section in our Google Classroom. till then, take care and be prepared for the exams, because exams will happen as far as my knowledge goes. Okay, so thank you.